Okay, so we're recording now, I think. And let me get rid of these photos and get to the right page. Okay, so basically we're talking about Bessel functions of the second kind. Um, so let me first once again ask, does anybody have a question? Uh, because we can certainly start first with a question. Okay, I think now I've got these damned photos keep coming up. It's very annoying. Okay, so let's talk about Bessel functions of the second kind. First of all, the Bessel functions of the first kind are those that are finite at the origin. That is to say, rho equals 0 or x equals 0, whatever the origin is taken to be. And on the other hand, sometimes the origin is not part of the physical region, and we need to allow for the possibility that that in the unphysical region, the function is infinite, or that the origin is in the physical region and the phenomenon that we're describing is infinite at the origin. In either case, one needs the Bessel functions of the second kind, which are represented as y nu, nu being an arbitrary real number. In fact, you might wonder, why didn't we start with the integral Bessel functions? The Bessel functions of the second kind of integral index. Well, the reason is that they're more complicated than the ones of non-integral index. Anyway, what we do is the y's turn out to be linear combinations or ratios of the Bessel functions of the first kind divided by a sign. And you can see when nu approaches an integer, the denominator goes to 0. So this is a singular limit. So the Bessel functions of the second kind of integer index are more complicated than those of non-integral index. As nu approaches n, what you do is you take the limit of the, by basically, well, you differentiate the numerator and the denominator with respect to nu. So in other words, as nu goes to n, the denominator is 0 plus whatever the derivative is of sine with respect pi nu respect to nu, and the same thing, the numerator is 0 apart from well, for nu minus n very small, this is proportional to the first derivative. And so then the nu minus n or n minus nu cancels between numerator and denominator. And so what happens is that you get yn as 1 over pi, the nth derivative of j nu, plus minus 1 to the n over pi, the nth derivative of j nu, both at nu equal to n and nu equal to minus n. And of course, the denominator, when you differentiate, you get cosine apart from a pi, that's this pi, and then cosine of pi n is then plus or minus 1, and that factors in with the derivative of the numerator and to give this expression. The functions, as I said, they all diverge as z goes to 0. Y0 is just a log, but the others are inverse powers of z. And that's how they are at near z equal to 0. And the figures, for example, illustrate that. Y0, 1, and 2 are here, and Y3, 4, and 5 are here. And what you see is that they diverge when rho goes to 0, but as rho goes to infinity, they start to have a wavy pattern. And in fact, the wavy pattern is it's like that of the Bessel functions of the first kind, namely it's 1 over square root of z times the sine of z, apart from some simple pi's. So that's basically the Bessel functions of the second kind. Now the Bessel functions of the third kind we've already met, namely these are the Hankel functions that we defined in chapter 8 as integral representations. These are integral representations of these Hankel functions. What you can see here is that this H1, which is a function of z and lambda, is given by this integral. And you can let z go into the upper half plane, where because then if you let z equal to x plus iy, you get e to the minus y times cosh. Cosh is always positive, and so you get decreasing exponential in the upper half plane. Over here, you have an opposite sign, and so you need to go to the lower half plane, where you'd have minus I times minus IY, and that would give you a negative exponential in the lower half plane. And when z and rho are both, z and lambda, sorry, are both, that z and that lambda are both real, then these two are complex conjugates of each other. The I and the minus I, the I and minus I and the I, and then the I and the minus I. And so they're complex conjugates of each other. These are called Bessel functions of the third kind. And it turns out that they're linear combinations of the Bessel functions of the first and second kinds. So they look like, now you can see that if lambda and if these functions j and y are real, then as they are for real z and real lambda, then H2 is a complex conjugate of H1. These are also called Neumann functions, and sometimes they're written with a capital N rather than a capital Y. And they're all infinite at z equals 0, and we saw that in this figure here. Let me make this bigger, the fonts. You guys could shout out and ask me to make it bigger, and then I would, because, you know, I can forget things. We've been thinking of z and lambda as arbitrary complex numbers, but in fact, if z is purely imaginary, what we get are called modified Bessel functions. So the Hankel functions turn into modified Bessel functions. And two examples of that are JA of IX. So this is the Bessel functions of the first kind, but here we're taking a Hankel function and making a modified Bessel function. So we saw this one earlier in the chapter, but in terms of a Hankel function, we get the K's like that. Some simple cases are that I minus a half is a cosh divided by a square root. I plus a half is a sinh divided by a square root. And k sub 1/2 is e to the minus z divided by z, apart from an overall factor. Once again, you don't need these functions if you're representing something that's finite at the origin. And but if the point r rho equals 0 is outside the region of physical interest, or if the phenomenon is infinite at that point, then you do need them. An example where they're important is coaxial waveguides. There, if you have an idealized coaxial waveguide, you've got something that's perfectly conducting inside a center cylinder that's perfectly conducting, and then a shell that's perfectly conducting. And the waves occupy the middle region, which I think for structural regions is typically plastic. Anyway, the points rho equals 0 are not in the physical domain of the problem because we're trying to figure out what the electric and magnetic fields are in the region that's either vacuum or plastic. And so we have to include Bessel functions of the second kind as well as Bessel functions of the first kind. And it turns out that the Bessel functions of the second kind come in with the same argument, essentially, as those of the first kind. The electric field is, we take z as the direction straight down the cable, and so the z and t dependence, t being time, is e to the I k z minus omega t, and that's multiplied by an e of rho and phi. So it's the z component of the electric field then is a linear combination of jn and yn. You have a similar equation for bz, and the fields E and B have to obey the boundary conditions of example 3, but also the boundary conditions at the so let me bring up notes and bring up notes and go to where we were at the end of notes. So what we've got now is what we've got basically is a conducting interior and then a cylinder. This region here, or let me go to blue, this region in here is some sort of plastic, and on the other hand, no, I'm sorry, I got that exactly wrong. That region is just copper. So let me erase that, go to yellow, and so I'll make this copper, and this is also copper. And so this distance here is R0. Anyway, these the tangential component of E and the normal component of B have to vanish at R0, and so the normal component is the rho component of B, and on the other hand, for E, it's the Z and the phi component, the Z component being this way and the phi component being that way. And if we're talking about TM modes, which have BZ, the transverse magnetic moments, which have the magnetic field only transverse to the direction of the cable, then the boundary conditions at R0 and at R can be satisfied. So we've got two boundary conditions there, and they can be satisfied if we pick this linear combination to vanish. And there V is R, the outer radius divided by the inner radius. So the outer radius here, this is R, and the inner radius is, of course, rho. We take the ratio, we call it V. And then we set X equal to square root of omega squared over K squared over C squared minus K squared times R0. And so then if we go to the case n equals 0, and we just choose V equal 10, that strikes me as rather a high number, but I think in coaxial cables is less than that. Actually, I don't really know. The first three solutions then are x01, x02, and x03. The are 0.33, 0.68, and 1. For n equals 1, we get 0.39, 0.73, and 1.07. And these are then the frequencies. So that's how the coaxial cables go. The spherical Bessel functions of the first kind, well, as I said to you many times, the spherical Bessel functions are much nicer functions, and the reason is that they have they occur in systems that have spherical symmetry, and so they're simpler functions. And in particular, they look as though they're more complicated because J sub L of X is square root of pi over 2X times J of L plus a half times X. Let me just write that as L. I'm making a note to myself. And you might say, oh, this is even more complicated, but in fact, it's much simpler. What happens then is that, well, first let's just see what happens if we take this expression and substitute it into Bessel's equation. And then as one of the homework problems is that you can show that the spherical Bessel functions then satisfies this differential equation. And this is the equation for a spherical Bessel function. And this is an equation we ran into in example 7.7 when we were talking about separable equations in 3 dimensions with spherical symmetry. And in particular, we were looking at Helmholtz's equation, which is minus Laplacian of V is K squared V. Notice the Laplacian is intrinsically negative, so minus Laplacian gives us something positive, K squared. And what we do is we can write R squared times the Laplacian in this way, divide by V, letting V be R theta phi, and then we get this structure here. We set e to the im phi equal to phi m as e to the im phi. That means that phi double prime over phi is just minus m squared. We take capital theta to satisfy the associated Legendre equation. And then the product R theta phi will obey this equation, which is Helmholtz's equation, as long as the radial function satisfies this equation, which it will if the radial function is JL of KR. And so the difference between this and this is that here, instead of X, we have KR. And so the solution then oh God. The solution then is JL of KR times YLM of theta phi, YLM being the product of capital theta to capital phi. So once again, I haven't explained why these things are simpler. Well, they're simpler because Rayleigh showed us that the spherical Bessel function of index L was simply -1 to the L, x to the L, and then this operation here, 1 over x d by dx, done applied L times to the ratio sine x over x. Notice that sine x over x is well behaved at x equals 0 because at small x sine of x is equal to x. And in particular, then, Rayleigh's formula gives us that J0 is just sine x over x. J1 is sine x over x squared minus cosine x over x. So these are really very, very nice functions compared to the spherical, cylindrical Bessel functions. And Rayleigh's formula, or we probably should say Strutt's formula, leads to this recursion relation. And in fact, the recursion relation can be used to show that the Bessel functions defined in this way satisfy the differential equation, this equation with x equal to kr. The series expansion for Jn and the definition of JL gives us for small rho this approximation, namely it's rho to the L over 2L plus 1 double factorial. So 2L plus 1 double factorial, of course, is 2L plus 1 times 2L minus 1 times 2L minus 3 and so forth. How does JL behave at Rod's rho? JL of rho behave at Rod's rho? Well, we use Rayleigh's formula, but what we do is we do a trick. We have the derivatives act only on the sign, and we throw away the terms where the derivative acts on x, because what happens is this, as you see, is x to the minus 1. You differentiate it, you get x to the minus x to the minus 2, and then you differentiate again, you get something proportional to x to the minus 3, and so forth. And that means that the terms that where the derivative acts on 1 over x get smaller and smaller for big X, whereas the derivative, when the derivative acts on sine, it just gives you a cosine, you act again, you get sine again. And so for large rho, the spherical Bessel function is -1 to the L the rho to the L's cancel. We get a 1 over rho, and then we have L derivatives of the sine of rho. Well, each derivative then turns a sine into a cosine or a cosine back into a sine. And you can verify that, in fact, that is, that's the same thing as, well, in any way, you can verify that this is equal to that, because the shifting by pi over 2 turns a sine into a cosine or minus a cosine. And the quality of this approximation is shown in figure 4. And so this is J1. There's the approximation for small rho, namely it goes as rho to the 2L plus 1. Let me just recall that for us. Where the hell is it? Jesus. No, it's rho to the L, sorry. Rho to the L for small l. And then for larger L, it's a sine rho minus pi over 2 rho. So this shows you the dot dash is the approximation for large rho, And so by rho equal to 10, it's pretty good in both cases. And the rho to the L is just here. This is rho squared. And this is a straight line, just rho. The wild animals in the background are two of my grandchildren. So let us go back to where we were. Okay, so this shows you how nice the spherical Bessel functions are. We can write the spherical Bessel function in a self-adjoint form, and then it takes this form, and we see the weight function is rho is r squared, the eigenvalue is k squared, and so maybe let me just remind you what happens here, namely for what we have for in general, oh God, I don't know why this defaults to so often to the eraser. Anyway, what we have is an expansion delta of x minus y. This is in general, it's rho to the alpha of x, rho to the 1 minus alpha of y, sum over I from whatever it is, 0 to infinity, ui of x, ui of y. And if these are complex conjugated, if these are complex functions, one of them is the complex conjugate. So you write a star there, basically. This is for when they're normalized. So let me put in a star. And we're talking about some interval here, a to b, and this is delta ij. So that's the normalization. Alpha is an arbitrary number less than 1 or equal to 1, greater or equal to 0. So that's the completeness relation, or the delta function relation, for the eigenfunctions of a Sturm-Liouville system with weight function rho. So let's see. So that means then that we can expand things in terms of a delta function. And here's our normalization, JL. Now let's be a little bit careful here. We have here eigenvalue k squared, and the k in this case is ZLN over A. ZLN is the nth zero of JL, which is stated here. In other words, JL of ZLN R over A is equal to 0 for R equal to A. And so in that case, then we have this orthogonality relation, and this is a self-adjoint system on an interval. In this case, the interval is 0 to A. So if I do go to the eraser, well, actually, I should leave this the way it was, because it really is, that's general. Whereas here, what we've got is 0 to A, JL. Now, the eigenvalues, you see, are ZLN over A. That's the eigenvalue being k squared, and k is z over A. And so what you have then is you have an infinite series of eigenvalues as n goes from 1, the lowest one is 1 because it's the first 0 of JL. And these eigenvalues are Well, you can see what the eigenvalues are just by looking at the formula for JL of rho at large rho. You see the eigenvalues are L over 2 or L pi over 2. And so let's see, where was I? So what we've got is basically, well, it's n plus L over 2 pi and squared. And so as L goes to infinity, this goes to infinity. And so these things are complete in the mean as discussed in section 738. And the expansion of the delta function that's analogous to this equation is, in this case, it looks like this. This is rho to the alpha, rho to the minus alpha, rho to the 1 minus alpha, I should say. And rho being r squared. And so the deal is that altogether what we've got here is rho squared, which is r squared. I mean, setting r equal to r prime, we've got an r squared, which is rho r squared. And then the 2 and the a squared are related to the normalization here. So this is the sum for the delta function, and that allows us to expand any twice differentiable function that vanishes at r equal to a, like this. And in fact, it also vanishes at r equals 0. Since all the since the JLs go as r to the L, these are functions that vanish at r equals a and r equals 0. So we can write an arbitrary function that's twice differentiable, vanishes at r equals 0, r equals a, as r to the alpha times this sum. And actually, r to the alpha, actually, I think that should be r, alpha should be 2. So let me just recall that. What are we supposed to have here? We're supposed to have, oh, well, I've already written it in this way. Okay, so I'm taking advantage of this very general expression. So what we do is we write it as r to the alpha sum an JL of z ln times r over a, and then the coefficients an is given by a normalization factor times an integral with the weight function. We've got an arbitrary alpha there, and we integrate the function we wish to represent like that. On an infinite interval, these things change somewhat, and they become a delta function of k minus k prime is 2k k prime over pi. And then we're doing it, instead of integral from 0 to a, we go from 0 to infinity. The weight function is r squared. And so that's in terms of k, but we can also write them in terms of r and r prime. And so it looks like this. So in other words, when we have JL of KR, we can think of k as the eigenvalue and r squared as the weight function, or we can think of k as the variable and r as the eigenvalue, and then the weight function is k squared. Schwinger had an amazing, he was simply a magician with mathematics. And he was able to, for example, one of his tricks was to write 1 over z dz e to the times the integral of e to the ikz. Well, d by dz brings down an x. Then x comes about from dx squared gives you an x if you divide by 2. Then if you integrate by parts and drop the surface terms, which you can because x squared minus 1 vanishes at the endpoints, you get the integral of x squared minus 1 d that. And if you take the differential of that, it's e to the I zx dx times a plus I and a z. The z cancels, the minus I goes away, and you get that. Well, so this was one of Schwinger's million tricks. And what you can then do is write 1 over z dz, or 1 over z d by dz to the nth power acting on this integral gives you this expression. And that's quite plausible. And then you then use Rayleigh's formula together with this expression for sine z as an integral, so that then you then apply Rayleigh's formula again to get the nth spherical Bessel function, and you have you write the sine as an integral. You then hit it with 1 over z d by dz using Schwinger's trick, and you get that. And then you see that z to the L is the nth derivative of, with respect to x, of e to the I z x. And so you're at this stage. Now you integrate by parts L times, you drop the surface terms, and you get something that contains Rodriguez's formula. And so this JL turns out to be an integral of a sort of a kind of a Fourier transform of a Legendre polynomial. And I mean, who would have thought? Now, if you substitute z equals kr and x equals cosine theta, then this thing becomes I to the L, JL of kr is this expression. And this is something that's used a lot in scattering theory, because previously we had an expression for e to the I kr cosine theta. Let me maybe go back to that just to sort of remind people of it. This was just using the completeness and orthogonality of the Legendre polynomials to write an arbitrary function as a sum of Legendre polynomials. Well, now we know that integrals of Legendre polynomials are related to spherical Bessel functions. And so we can jump to this. We can jump back to where we were. So let me try to get us to where we were. Sorry for all this. So we now take as the function f of x, x being cosine theta, this expression here, and now we see that the integral from -1 to 1 makes a lot of sense, because we're talking about Legendre polynomials, which are complete in that interval. And now we see that this integral of PL of cosine theta, d cosine theta, that's this thing, and that spits out a JL. So now we have an expression. This thing up here is really e to the I k dot r. Oh, God. This thing is really, so let me switch maybe to blue. In other words, e to the I k dot r is, of course, e to the I length of k, length of r, cosine of the angle between them. And so e to the I k dot r, which is the phase factor of a plane wave, can then be written as this Fourier Legendre expansion, and then Schwinger's trick gives us that this thing is actually a spherical Bessel function. And so if theta phi and theta prime phi prime are the polar angles of the two vectors r and k, then what we have is e to the I k dot r is this expression here. This thing gives us the PL. Let's see, what I'm a little puzzled at is to, oh, we use the addition theorem. Okay, sorry. What we've done here is use the addition theorem for PL of cosine theta. The addition theorem is this. In other words, PL of n dot n prime is a sum of the spherical harmonics, which we saw at the end of the last chapter. And so these spherical Bessel functions occur often in problems where you have spherical symmetry. And so if you have the scattering by a spherically symmetric potential, then you can expect that you may have spherical Bessel functions occur. So the Hamiltonian for a free particle looks like this. This has spherical symmetry. L squared, which is the orbital angular momentum operator, squared has spherical symmetry. And they both commute with the orbital angular momentum operator, but the different components of the orbital angular momentum operator don't commute with each other, so we pick one of them, LZ typically. And then H0, L squared, and LZ form a set of simultaneous, they're set of three Hermitian operators that commute with each other. Therefore, they're compatible operators in the sense of section 1.32, and they have simultaneous eigenvalues. Notice that I could equally well have chosen not H0, but H0 plus V. So let's see if I can get back to that. So we could have had H0 go to H, which would have been P squared over 2m plus V of R. And this is spherically symmetric. And so they would form three compatible operators. And then the wave functions then would be products of, well, in the case of H0, the wave functions are products of spherical Bessel functions and spherical harmonics. If we want these things to be eigenfunctions of H, including the potential, then usually the radial function is more complicated, and so it's not just a spherical Bessel function. So that's why I specialized to H0. And in this case, then, the inner product of the position bra with the ket KLM is K, JL of KR, YLM of theta phi. They satisfy this normalization condition. And in other words, you just write these two as you insert a complete set of states, R theta phi, and the bra gives us JL of KR, YLM star of theta phi, and the ket K prime L prime M prime gives us JL of K prime R, YL prime M prime. And now we have the orthogonality in L and the L and M over here. And then this gives us an orthogonality, a delta function of K minus K prime. This is equivalent to the completeness relation, integral over momentum, and then a sum over angular quantities, angular quantum numbers. And the inner product of a free particle K wave function with the K with a with the KLM is a delta function times Y star of theta prime phi being the polar coordinates of the vector K prime. If we use this delta function, which is just that, we can take that expression, this expression, in other words, and stick it in here. In other words, what we have here is e to the I k prime dot r prime over 2 pi to the 3. This is a 3/2. This is then r, and now we've got a big sum, r, and the sum is KLM, KLM, and this, do I have this right? Right, this is r, and this then would be k prime. And now that I realize this, this is a sum over L and M, but it's also an integral, Decay, and so that's the expression for, that's this expression here for the identity operator, and then this gives you integral Decay, these two inner products, and this one gives you JL of KR YLM, and this one just gives us a Y star LM times an I to the L over K. And let's see, I'm just wondering what happened to the integral. Right, there should be an integral over K here. All right, I better check that equation, 10.109. So that's an integral Decay. And so this is that. We still have to, so there should be an integral here over K. If this is K prime here. Oh, well, there's a delta function here, though. That's the point. There's a delta function here that, all right, so I was being sloppy. This thing gives us a delta function, and that turns the integral into just a 1 over K. And the 1 over K, I'm just wondering where the 1 over, the 1 over K cancels this K up here. So that's what's actually going on. Okay, so the small KR approximation, remember for small KR, for small rho, the spherical Bessel function goes as rho to the L. And consequently, this wave function at small KR, so low momentum and R near the origin, this thing is KR to the power L. And so that means that for small k and small r, this is only important for very small L. And so the probability of a particle with angular momentum h bar L about the origin r less than 1 over k is the integral of the square of this wave function out to r. And when you do that, you get something kr to the 2l plus 3. So it's very small for big L and small momentum. And what that means then is that a short range potential can only affect, short range means that the scattering would only be for R very small because it's short range. And then if you're at low energy, so K is also small, then the only values of L that contribute are very small values of L. And so this was used by physicists doing nuclear scattering way back in, I guess, the 1930s. And what they found was that nuclei scattered low energy hadrons into S waves. That is to say, see if I can bring this up. So let me switch to maybe green. So in other words, they would have a proton or something come in, and they would have a nucleus here of some sort. And what would happen would be that the scattering would be spherically symmetric, and at least in a suitable rest frame, it would be spherically symmetric. And the conclusion then was that that nuclear forces are of short range. And that gave the Japanese physicist Yukawa the idea that that the potential was something like e to the minus mu r over r, where mu is the mass of some intermediate part of an exchanged particle, an exchanged boson. And he then, or I don't know if it was he or others who said, well, it's got to be the muon because the mass of the muon is 105 MeV. But people realized that the muon does not interact much with, only interacts electromagnetically and weakly with nuclei. And so it was actually pi mesons, which have a mass of around 140 MeV and come as versions pi plus, pi 0, and pi minus. This triplet of mesons interacted, are the exchanged, in effect, the exchanged particles of low energy hadron scattering. So let's see, let me just check to see how far we are. All right, so we're at in the right place, I guess. So let's suppose we have a potential V of R of short range. Then our wave function at large distances should look basically like a free particle because it's no longer being affected by the potential. And so it's basically sine kr over minus L pi over 2 over kr, and that then expanding the sign just gives us this. And so the difference between the true scattered wave function and the free particle wave function is then basically a phase shift. And in fact, if the total cross section for scattering then at low energy is just an infinite sum of the squares of the sines of the phase shifts. This is explained very nicely in a book by Tanuji and his two collaborators. Incidentally, that's an excellent textbook. It's Tanuji, by the way. Tanuji won the Nobel Prize in Physics for work in optics, and it's a funny book. It's quite long. You have volume 1 is about so thick, and volume 2 is about so thick. On the other hand, the principles are all carefully and completely explained in the chapters. And if you put the chapters all together, you'd have something that would be about so thick. So you can read the book, you can read the chapters of both volumes and learn essentially all of quantum mechanics. And then you can read as many complements as you have time to read. Anyway, it's an excellent textbook. Once when I was teaching quantum mechanics, I said, well, you should read the chapters, and if you read the complements, it'll do you no harm, it'll do you some good. One person read the complements, and that was a young woman who, it turns out, had graduated from West Point. And so discipline and making serious efforts were things that she had learned to do. And so she read all the complements and learned a hell of a lot of physics. Okay, I think the last topic in this chapter, oh no, we've got a little bit more to go. So I need to, all right, let me do quantum dots quickly then. This is just the view of quantum dots from 30,000 feet. Here's Schrodinger's equation. And we're imagining, we're thinking about quantum dot as, well, first of all, what is a physical quantum dot? For example, it might be a cadmium selenium sphere, radius less than 2 nanometers, so very tiny object. A very tiny object, and photons from a laser then can excite electron hole pairs, which then radiate in nanoseconds. So we can think of this quantum dot simply as an electron trapped in a sphere of radius A. So this is the eigenvalue equation, and you wouldn't be surprised to learn that this is a spherical Bessel function times a spherical harmonic, but there's a boundary condition, namely that the thing vanishes at r equal to a, and we can put in a Heaviside function to make that, happen. And so then if we apply, and we can imagine that this potential is, for simplicity, we can say that it's 0 for r less than a and infinite for r greater than a. And in that case, this thing inside, for r less than a, we can drop this term, and we know these are exact wave eigenfunctions for r less than a. And then we differentiate, and we see that basically it's, second derivative with respect to r pulls out z over a squared. So the energy is basically h bar z over a squared over 2m. And and the eigenfunctions then are, or the eigenvalues, the zeros of the spherical Bessel functions are z0 comma n are equal to n pi, exactly, in fact. And so these are the lowest eigenfunctions. If the coupling to photons looks like p dot a, then you expect delta L equal to 1. And so then the difference between the n equals 0 and the L equals 1 state is E n10 minus E100, and that's, so the n equals 1 state is, would have a Z1, and I don't know why I have an n there. So let me say I should look at 1016. Anyway, if one puts in the numbers correctly, what one finds is that these should fluoresce at red light if A is 1 nanometer, and if A is between 1.2 and 1.5, then you get another 0 comes into play. And all right, let me go on to Bessel functions, spherical Bessel functions. The second kind, this is when the origin is not in the physical region or the phenomenon is infinite at the origin. Rayleigh's formulas give them as, again, a very simple expression. You know, what's not to like about this, especially if you've seen cylindrical Bessel functions, which are those nightmare infinite series, one of them involving a log. So the term in which all the derivatives act on the cosine is the one that dominates for large rho, and that gives us basically cosine of rho minus L pi over 2 divided by rho. At small rho, what do we have at small rho? We have 1 over rho to the L plus 1. And let's see if I can just eyeball that. For small rho, we would differentiate 1 over rho L times, and we would have 1 over rho to the L plus 1, sure enough. And then these rho to the L powers cancel. These are all infinite at L equals 0. Here's J1, here's J2. They become basically sine function or cosine functions. Anyway, trig functions at large argument and 1 over rho or to some power at small arguments. And one example of the use of these is scattering over a hard sphere. And so the idea is that the potential we can imagine is infinite when r is less than the radius of the sphere, but 0 elsewhere, and that's given by this expression. So then for r greater than r0, in other words, outside the sphere, you have as eigenfunctions a linear combinations of JL and YL, and the fact that the y's are infinite at r equals 0 is no problem because r equals 0 is not part of the physical region for the scattering problem. We imagine that the particles never penetrate the sphere. And the boundary condition that UL of R vanishes when KR 0, that UL of KR 0 vanishes, fixes the ratio of DL to CL. And well, I don't know if we need to go through this in detail, but what you find is that for L equals 0 and using Rayleigh's formulas, what we see is that KR0 is C0 sine minus D0 cosine, and D0 over C0 then, if this is 0, is tan of KR0. So the S wave then has is U0 of KR, C0 sine KR minus KR0 divided by KR cosine. And so there was a little arithmetic here, or trig. And so the phase shift is has a tangent that's minus KR0. And the cross section at low energy then is 4 pi R0 squared. So that's the sphere itself. If I can get the damned, the sphere itself has a radius here that's R0. And so the area that it subtends for particles coming this way is pi R0 squared. So you might think that would be the cross section, but in fact, the cross section at low energy is 4 times that. So if you go through the details here, you can realize that. And the tangent of the P wave phase shift is this, P wave being L equals 1. And so that gives us KR0 cubed over 3. And the L phase shift is KR0 to the 2L plus 1. And so if the potential is of short range, Then at low energy, namely K less than 1 over R0 in natural units, the phase shift is given by this expression, and we see that the phase shift is smaller and small. If KR0 is small, in other words, R0 is small, low energy, the phase shift is very small because the phase shift for high L is very small. And even for L equals 0, it's proportional to KR0, which is itself a small number. But it's again, it's what you're seeing is that basically you have S-wave scattering at, in other words, L equals 0 is the dominant scattering, because for L equals 0, what you have is the phase shift delta 0 is something like KR0, and delta 1 is something like KR0 cubed, 2L plus 1 or 3. Okay, so we're done basically with this chapter. On the other hand, we haven't had any questions, so let's see if somebody can figure out a question to occupy the next 7 minutes of class. Also, we could discuss, well, if nobody has a question, then we can discuss what we should do next. And what we've got then is we can do group theory, we can do relativity, probability statistics, Monte Carlo methods. The AI chapter is very short. You can just read it on your own. Order chaos fractals is also very short, and you can read that on your own. Strings is quite short. Path integrals is a long chapter, and it is more advanced than some of the other material. I actually think that I think you all know the basics of special relativity. What I'd suggest is for me to do a quick review of special relativity and some of general relativity. The thing about general relativity, you see, is that there's a basic idea that's very simple and very important. And you can learn that basic idea in 15 or 20 minutes. And then, in a sense, you understand general relativity. On the other hand, Monte Carlo methods are of real use, and these are things that, well, I can certainly go through this chapter. So let's see, I was keeping score of the votes earlier, and I'm getting 2 more votes for Monte Carlo, but are these people who voted previously? You know, I don't want Trump to get, all right, because Trump would get after me for counting votes twice. All right, so now we have then, I'm counting then 2 votes for Monte Carlo, 2 votes for relativity. So I think what might be a nice compromise would be to, we actually have several classes left. I could do Monte Carlo methods. I could start them Wednesday. Of course, Wednesday is a 468 class, so if you can discuss whatever you want. You can have me discuss whatever you want, any of the remaining classes. But what I can do is I can start Monte Carlo and then be interrupted by questions on Wednesday and Thursday. And I think I can finish that chapter. And then the following week, I can do special and general relativity. Let's see. I don't know. I'm thinking of not assigning any graded. I'm thinking of not assigning graded homework for these other chapters. I want these other chapters to be basically fun. What you could do is you could either by yourself or with one or two friends or enemies, you could get together and do a little project on Monte Carlo. I think you'd learn enough by Thursday to do a little project on your own, a Monte Carlo project on your own, which might be amusing, or conceivably, you might learn enough relativity to do a little project there. And that I could give you extra credit for those things. But no, I'm certainly not going to have, going to assign any graded homework on them. I want the last sessions on these other things to be basically fun. And in view of the pandemic, there are going to be no exams in this course. I expect that you might have suspected that. Yes, I see some applause. I think that's the only appropriate thing. We certainly can't get all of you together in a classroom and proctor you. And so the grades are going to be on homework, and my understanding from the grader is that the grades will be high based on homework. And this has been a hell of a semester because of the pandemic, and so something ought to turn out well. So, all right, so we'll do Monte Carlos starting tomorrow, but if you, but by all means, it's okay to ask questions about linear algebra, vector calculus, Fourier analysis, infinite series, complex variable differential equations, integral equations, Legendre polynomials, Bessel functions. You can ask questions about those in any class, and you can just interrupt with the chat. And if I don't see the chat, you can shout and tell me to look at the chat. So I think that's what we'll do. By the way, if you want to do a project on Monte Carlos, you ought to, I think you ought to, well, I would recommend having a Fortran compiler, which you can download free from one place or another, or a C compiler. On the other hand, MATLAB, I think, has built-in Monte Carlo routines. So that makes projects much more accessible and more fun. And I've always written my own Fortran codes for Monte Carlos. And so maybe I'll learn something from you guys if one of you has an amusing project that, in fact, if you want to send me an email about it, or you could just present it in a Wednesday class, and if we're worried about FERPA, we can not put it on the YouTube website. All right, so we're just about out of time. Right, somebody brought up Mathematica and Python. Python is free and very, very good. And in fact, one of my sons is a computer scientist in industry, and he said that anybody who knows mathematics and Python can get a very good job. And so that's Oh God, you want to know something about, somebody wants to know something about projected grades before undertaking the optional project. Oh God. Well, I don't know. I mean, we can't know for projected grades until we've finished all the homework assignments and had them graded. Um, so I would say, you know, I would say do the project in order to learn something and in order to amuse yourself, or to show off or whatever. But I don't know. I mean, grades, you know, uh, it's what's important is what you learn, not what your grades are. When you people getting PhDs forget about what their grades are, and nobody, and I think people doing hiring don't know what people's grades were. So but you know, maybe I'll talk with the grader and see if we can have I might ask him to, he and I can get together and send you all some possible estimated grades. But I don't know. My habit in the past is not to make up the grades until everything is done, and then I sit down and I look at how everybody did and make some sort of an estimate as to what is fair and generous. All right, well, we got to stop this class. So goodbye, everybody. Have a nice evening, and stay out of bars, for God's sakes. So I'm going to stop recording.